He's giving me a death stare. Okay.
It's okay.
Okay, so we're learning about the senses. So I'm going to try to prove to you, well, not prove to you, I'm going to try to convince you that what you're perceiving isn't actually reality. Yeah?
Okay.
All right. So the first sense we're going to touch on, is touch. So what happens is that there are receptors on like your skin that when you touch something, it converts it to electrical impulses and it acts as a transducer. So and then your brain interprets it as like good touch, bad touch. Like there's different touches, different receptors for different things. Like there's like pressure, like there's poking, vibration, like hot, cold, stuff like that.
Okay.
So like an example would be like a PA system. It takes like the sound waves and transduces them into electrical energy. So these like all your receptors can
You're good.
they can transduce light, changes in temperature, sound waves, physical objects that you can interact with, and then like molecules in the air or like in your mouth. So you don't try to taste the air. So with pain, there's these things called nociceptors, and then those are receptors of a sensory organ that detect any like potentially harmful stimuli.
Okay.
And so, like, pain is actually all in your head. Like,
Sorry.
your brain like interprets pain like as just like something like bad and like you should stay away from it. So like it kind of like teaches your body like stay away from things like like a hot stove or like a sharp needle or something like that.
Okay.
And then there's different types of fibers. So there's an alpha delta fiber which is myelinated. So that means it has like it's like wrapped in like a myelin sheath.
Oh.
If you know what that
Okay.
is.
Yeah. No, I've heard about that before.
Okay.
Yeah.
Sophomore year science. Or
Yeah.
something.
Right. Yeah. Yeah.
So then that shows like an initial sharp pain.
Okay.
And then there's the C fiber, which is unmyelinated, and that's like a throbbing, less intense pain.
So why would the myelin sheath make a difference? What does that do?
So
If you don't mind
myelination, so myelination allows it allows like signals to like travel faster. So like it's
Okay.
an initial sharp pain that only goes away really quick.
Sure.
But like when it's not myelinated, like that's what like the throbbing is for.
Okay.
So, interesting fact. So when you eat like things like habaneros, for example, like they're a very spicy pepper, and what happens is like when you eat it, it actually causes conformational changes, and it opens receptors that go to your brain, and your brain interprets it as your tongue is on fire. So that's why
Okay.
spicy food is spicy, because your brain literally thinks your mouth is on fire. Pretty interesting, huh?
Sure. Yeah. Okay.
Yeah.
Yeah.
Same thing with like menthol. It just makes your body think that it's colder than 71 degrees Fahrenheit, I believe. So the next sense we're going to talk about is hearing. So hearing, like mechanoreceptors are responsible for that. Like they respond to small changes in mechanical force. So in your ear there are these things called hair cells, not like the hair on your head.
Right.
But they're like hair cells. They're actually, I have a picture. I drew it. So these are the hair cells. Okay, I'll show the picture I drew. I drew a neuromast organ right there. This is a neuromast organ. So the hair cells are the things with the little cilia, which are like the little strings.
Okay.
And when the sound comes in, they change, or they move only one direction, and they're pulled open, so then the cascade can happen, and like it amplifies sound.
Okay.
So so talking a little bit about fish, they have what's called the lateral line system, and that helps detect like water currents and
Yeah.
stuff. You know what that is? The little line down.
Yeah.
You smarty pants.
It's how like they swim in schools because they can detect each other's movements so well. And
Well, I didn't know that.
Oh yeah.
So, as mammals, we use our vestibular apparatus
What's
to.
that?
It's the inner ear. So, okay,
Okay.
so here's a chart. So this is the inner ear.
Sure.
So we use it to determine equilibrium, like whether or not we're moving. So we have 3 semicircular canals, and
That's why when someone like ruptures an eardrum, they can just tip over because their equilibrium.
yeah.
Yeah. Yeah.
Yeah, so like they're semicircular canals, which those determine angular acceleration, which is like rotation.
Mm-hmm.
It's like spinning,
Yeah.
stuff like that. And then there's maculae. Those determine linear acceleration. And in the macula, there are these things called otolith, which are these. They look like little beads or little rocks in your ears.
Yeah.
And those help maintain your balance. So when these if they dissociate,
Sorry.
if they dissociate, you can have things like vertigo, dizziness, stuff like that. It's
Yeah.
pretty cool.
Yeah. No, vertigo's not cool.
No, vertigo is not cool. I fainted from vertigo. So how do we hear? So there's a vagina, which is this.
Mm-hmm.
And this contains the organ of Corti, which is like this whole thing.
Yeah.
And let's see, and it goes to the brain via the auditory nerve. And when we hear, and when the vibrations get sent in, this is the stapes, and it pounds against this, and the sound travels down. And then you hear, here's this. You hear higher frequency sounds in the stiff areas, and
Sure.
you hear lower frequency sounds in the more flexible areas.
That makes sense. Yeah.
So basically, your brain just interprets vibrations for hearing. So it's
Yeah.
pretty cool.
Yeah. Suppose you don't really think about it that way, just because you're always hearing.
Well,
you have
yeah,
an
you're always
understanding,
hearing. But vision is even cooler. Stay tuned. So we'll move on to that one next. So we have receptors that are stimulated by light, and our eyes focus on these receptors. And the millions of receptors in your eye, they allow an image to be formed. And what does the image look like? It depends on what stimulates your receptors. So what I see might be completely different from what you see, because literally it's just taking light and bouncing it back into our eyes. And our cornea is like refracting light, and our lens is refining it.
Mm-hmm.
So here's the eye. It's the cornea, and that's the lens. So the cornea takes it in, lens refines it. Let's see, where are we at? So, okay, sorry, back to the structure. So the outer layer is a sclera. It's like a tougher, it's like a tough outer part of the eyeball.
Sure.
Um,
Good.
yeah, I just had a hiccup.
Okay.
Yeah, so the sclera, and then there's the cornea, which is the clear part of the eye. So if you've ever looked down at a cat's eye, you see how it's clear.
Mm-hmm.
That's the cornea.
Yeah.
So then the middle layer is the uvea, and it has 3 regions, which is the choroid, ciliary body, and iris. And the iris is the colored part of your eye. It's a smooth muscle that contracts and dilates in response to wavelengths. So let's see. Okay, and then there's the inner layer, which is the retina, and that has 3 cell layers, which is the photoreceptors. And the photoreceptors are rods and cones.
Mm-hmm.
Rods are more for night vision, black and white, and cones are for color stimulation.
Sure.
And let's see. So rods have something called rhodopsin in them, while cones have photopsin, and these are both light absorbing pigments.
Mm-hmm.
So for an example, when you're shifting your eyes, let's say you're outside and you look up at the stars at night,
Yeah.
when there's no light pollution, but
Right. There was a meteor shower last night that we missed. Yeah.
so let's say you're looking up in the sky and you look at a star, but have you ever noticed in your periphery the star in your peripheral looks brighter than the one that you're looking at, and then you shift your eyes to look at it and it looks duller?
Is it because you focus on it?
Well, okay, so that happens because there's a fovea in your eye, which is an indentation in the retina, which is where the low light hits.
Yeah.
And the fovea is cones, so it doesn't do as well in night vision.
Sure.
But it won't be as stimulated as the rods in the other part of your eye.
Okay.
So there's a super cool concept called bleaching. So have you ever seen those trick things where you stare at something for a really long time, and like, you know, for example, like there's a red piece of paper and you just stare at it, stare at it, stare at it, and then you look the other way, and then, you know, a bunch of things are red?
Mm-hmm.
That's called bleaching.
Hmm.
Because basically you've maximally stimulated all your photoreceptors.
Interesting.
Yeah, it's pretty cool.
So you get a big spot when you stare at the sun?
I think so, yeah.
Yeah, probably the same concept.
I mean, really shouldn't stare at the sun.
No, no, obviously not. Or you know, you get a bright flash or something and you see
Right.
it for...
Yeah.
Anyways, okay.
So most mammals are dichromatic, but humans and apes are an exception. We got a secondary trichromatic thing. So that's red, green, blue.
Hmm.
So we have the ability to see like a lot of different colors.
Okay.
There was a super cool picture that I saw that would like, you know, like bees see like UV and like
Hmm.
it's super cool. We see literally nothing compared to like
Most.
so many things.
Yeah, yeah.
So for as far as depth perception goes, we have a trade-off between like depth of field and breadth of field. So there's monocular vision, which is like, think of a fish, you know, they have eyes on the side of their head basically.
Yeah,
So
yeah.
like they can't really see in front of them, so they don't have much depth perception.
Yeah.
But they can see like all out the side.
Mm-hmm.
But like for us, we our visual fields overlap, so we can see like much further depth wise.
Yeah. Well,
But
yeah.
we can't really see far past, like, you know, we don't have very good periphery.
Yeah.
So for visual information, it's all input to the tectum,